Hello, on today's video we want to introduce the parameter variation method for solving second order linear differential equations with no constant coefficients. Okay, so first of all we need to establish what is the form of this kind of differential equations that we want to solve. In this case, the form of the general differential equation of this type is going to be of the form a sub 0 of x times y double prime plus a sub 1 of x times y prime plus a2 of x times y equals some function that I'm going to name as h of x. Okay, so we wonder how would we be able to solve this kind of equations? Well, that is what we want to do in this video. We are going to deduce a method that will help us to solve any kind of differential equation of this form. So what we want to do first is to divide by a sub 0 of x all this equation. If we do that, we are going to get the next y double prime plus a1 of x over a0 of x times y prime plus a2 of x over a sub 0 of x times y equals to h of x over a sub 0 of x. And what you need to notice here is that these functions that are the coefficients of y, well, are also functions of x. Okay, so we can rename all these functions that we got just to simplify things. And we are going to get the next equation, y double prime plus, let's name this, for example, as p of x. This is going to be g of x, and this is going to be f of x. And we are going to get that here we have p of x times y prime plus g of x times y equals f of x. So solving this equation is equivalent to solve this equation that we have here. And how are we going to solve this equation? Okay, well, first of all, we need to remember, if you have already taken some courses regarding differential equations, that we can establish a new equation that will be named as the homogeneous equation, well, associated to this differential equation, which is just going to be the next equation, y double prime plus p of x times y prime plus g of x times y equals to 0. Okay? Then, well, there are some methods that we can use to solve this differential equation, but looking that it's a second order differential equation, we can find, in this case, well, two different solutions for this equation that we are going to name as y1 of x and y2 of x, okay? Because it is a second order differential equation, so we have two solutions. Also, it is very known that in differential equations that are linear, well, what you can do is that if you have two linear independent functions that are solutions for the differential equation, we know that the linear combination of these two functions, well, is also a solution of the differential equation. So that means that we can establish a solution that is going to be named as y sub h, and h is for homogeneous, which is going to be defined as a constant c1 times y1 of x plus c2 times y2 of x. Okay? But recall that, well, this is just a solution for the homogeneous differential equation, and we want to find, well, the general solution for this equation that has, well, this function f of x here. Okay? So the parameter variation method consists on the next. We are going to establish that we can find a function y sub p, where p is from particular, is a particular solution, that will be defined as some function u of x times y1 of x plus a function b of x times y2 of x. Okay, we are going to postulate this, and let's see what happens. In this case, our objective is to find u of x and b of x, and then we will be able to get our particular solution y of p. Okay, so what happens if we substitute this in our differential equation? Well, you know that, well, we need to take first derivative on y. So what happens if we calculate that? Well, we are going to get u prime of x times y1 of x plus u of x times y1 prime of x plus b prime of x, y2 of x plus b of x times y2 prime of x. So here's the first trick that we are going to use. If we don't use this trick, actually, well, this method will be very complicated, but it will be very important to establish the next. We are going to say that u prime of x, y1 of x, plus b prime of x times y2 of x is going to be 0. Okay? So what we could say is that, well, the functions u and b that we are going to find, well, just they will satisfy this equation. Okay? So I'm going to just to rename this equation just by I'm going to avoid using x, just to write this as u prime y1 plus b prime y2 equal to 0. Okay, so this is a very important equation that we are going to use later. Okay, so that means that if this is equal to 0, then yp prime is going to be, well, u times y1 prime plus b times y2 prime. Then we can calculate yp double prime, which is going to be equal to u prime y1 prime plus u times y1 double prime plus b prime y2 prime plus b times y2 double prime. Okay, so now we have found the two derivatives that we needed to substitute in our original differential equation, which is, well, this one over here. Okay, so we see here that we need to put the second derivative of y, then plus p of x times y prime plus g of x times y, and then equal that to f of x. So if we do that, we are going to get the next: u prime y1 prime plus u times y1 double prime plus b prime y2 prime plus b y2 double prime. That corresponds to yp double prime. And then plus b of x times, well, yp prime, which is u y1 prime plus b y2 prime. And then plus g of x times y, but y is just, well, the product of u y1 plus b y2. So this is u y1 plus b y2, and this is equal to f of x. Okay, so if we keep developing this, we are going to get u prime y1 prime plus u y1 double prime plus b prime y2 prime plus b y2 double prime plus p, and I'm going to skip writing x again, and to get p u y1 prime plus p v y2 prime plus g uy1 plus g vy2 equals f of x. And here what we want to do is to factor u and v. We are going to take u as a common factor and then v as a common factor. So what happens if we do that? Let me check. Okay, we are going to get u prime y1 prime plus u times y1 double prime plus p y1 prime corresponding to this term, and then plus g y1, okay, plus b times, it will be, well, I forgot this term here. We are going to write it right here, and then we are going to factor b, and then we are going to get y2 double prime plus p y2 prime plus g y2, and this is equal to f of x. But look, what we established at the beginning of the video is that y1 is a solution of the homogeneous equation. I recall that, well, that equation was this: y double prime plus p y prime plus gy equals to 0. And we said that, well, two solutions for this homogeneous equation is y1 and y2. So that means if we take y1 into this equation, we are going to get 0. Also, if we put y2 in this equation, we are going to get 0, which is what we have in this case. So all these equations, well, these expressions actually are going to be 0. So in that case, where those expressions are equal to 0, we are going to get that u prime y1 prime plus b prime y2 prime, well, is going to be equal to f of x. Okay? And remember the other equation that we found, this one here? Well, now with that equation we can establish, well, a system of differential equations that we need to solve to find u and v in terms of x. Okay? So first, to be able to solve this system of equations, well, let's notice that, well, we can write this as y1, y2, y1 prime, y2 prime in a matrix representation, and a column vector of u prime times, b prime here, and then, well, this is going to be the vector 0, f of x. Okay, so now if you remember your courses for linear algebra, well, we are going to solve this by using the Cramer rule. Okay, so what does it say? Well, it says that here we can find u prime if we take the determinant of the next. We need to put here in the column places, we need to put 0 f of x, and then here we are going to put y2 prime and take the determinant of this, and then we need to divide this by the determinant of the matrix, of the coefficient matrix, like this one. So that will be y1, y2, y1 prime, y2 prime. Okay, so what are we going to get? Well, this is going to be minus y2 times f of x over, well, here we can calculate the determinant, but just to simplify things, we are going to define the function which is named Wronskian, w equals to, well, all this that we have here. it is going to be y1, y2, y1 prime, y2 prime. So, well, actually this is a function of y1 and y2. Again, its name is the Wronskian, a very famous function. So we are just going to write that here. Okay, so we get that u prime is equal to negative y2 f of x over w. And then, well, we need to do something similar with b prime. In that case, we are going to get y1, y1 prime, and then 0 f of x over, well, again, we are going to get the Wronskian here, and this is going to be equal to y1 f of x over w. So we get that b prime is equal to y1 f of x over w. So we are almost there. We now just found u prime and b prime, but we know that, well, if we have a function of x here, we can just take this as a separable differential equation. So we know that u prime is equal to the derivative of u with respect to x, which is negative y2 f of x over w, and that means that u can be defined as, well, negative the integral of y2 f of x over w dx. By a similar reason, we can define b as the integral of y1 f of x over w times dx. So, and now that we have found u and b, well, remember that we defined y sub p, which is the particular solution, as u times y1 plus v times y2, and this can be written as, well, negative y1 times the integral of y2 f of x over w dx, then plus y2, the integral of the integral of y1 times f of x over w dx. Okay, and recall that when you find the homogeneous solution and the particular solution, well, the complete solution is going to be equal to the sum of these two, y sub h plus y sub p. So that will be, well, y is going to be equal to c1 y1 plus c2 y2, and then plus yp. So that is going to be this expression over here. Okay, so this will be our final result. This is the general solution for a second order linear differential equation of the form that we defined at the beginning of the video. So if you have any question regarding this process, well, feel free to leave it on the comments, and thank you so much.